10, 9, 8, 7, 6, 5, 4, 3, 2.
Hi guys, this is Giancarlo Corpus and this video is all about the Omega Navigational System. So, in order to make this video more exciting, I'll put some scenarios wherein I can say that this system will be very useful. So, for the scenario, let's say you are traveling to Africa on a ship and then suddenly it was attacked by the pirates. The pirates killed the man that handles the navigation of the ship. However, the pirates find the ship very old. That's why the pirates leaves you out of nowhere after stealing all things inside the ship. So, what will be your plan? For the plan, maybe you are planning to starve to death or use compass. However, you'll find it very complicated in such cases. GPS, but assume GPS was not yet invented. So, for the last option, Omega Navigational System will be the one. Before proceeding to the application part, let's first talk about the Omega Navigational System. It was the first global range radio navigational system. Very long distance radio signaling is possible using long wave techniques with low frequencies ranging from 10 kHz to 13 kHz. This system was operated by the United States in cooperation with 6 partner nations: Japan, Trinidad and Tobago, Argentina, Liberia, Australia, and Norway. However, Liberia was replaced by the system. All in all has 8 Omega stations. Station A, Bratland Omega Transmitter in Norway. Station B, Trinidad Omega Transmitter in Trinidad and Tobago. Station C, Kaneohe Omega Transmitter in Hawaii, USA. Station D, Lamore Omega Transmitter, North Dakota, USA. Station E, Chabrier Omega Transmitter, Madagascar. Station F, Trulu Omega Transmitter, Argentina. Station G, Woodside Omega Transmitter, Australia. Station H, Tsushima Omega Transmitter, Japan. The position of the transmitters are well decided so that every position on the globe will receive usable signals from at least 5 stations. Though this system presents the best potential for navigation, some problems were needed to be addressed. At lower frequencies, the signal will reflect off the ionosphere and ground, allowing the signal to travel great distances in multiple hops. However, it is very difficult to synchronize multiple stations using these signals, as they might be received multiple times from different directions at the end of different hops. This results to some delay effect on accuracy, since we know that the distance is equal to speed of light over time, and that is when we assume that the speed of light is constant, which is 3 times 10 raised to 5 km per second. Let's say the receiver end receives the longer reflected wave, increasing the distance traveled by the wave, thus increasing the propagation time. Imagine if the delay is very large and the accuracy of the clock is 0.01% error. So, a delay of 2 seconds results to 0.0002 seconds, which is approximately 15 kilometers in terms of distance. After years of researching, the scientists finally found a solution in what's so-called atomic clocks. The transmitter and receiver end are synchronized with atomic clock set at a common standard time. The accuracy of this clock is equal to 10 raised to negative 14 of error percentage. That means it loses 1 second in 100 million years. For the working mechanics, each omega station transmit a sequence of 3 very low frequency in pattern of 10.2 kHz to 13.6 kHz to 11.33 kHz plus a fourth frequency which was unique to each of the 8 stations. The duration of each pulse is different in a fixed pattern and repeated every 10 seconds. Now that we know the concept of Omega Navigational System, let us apply this concept to our scenario. The first step is to find your location via station identification. Since each stations present unique duration and fourth frequency, it will serve as your identification of what stations are surrounding you. In our case, the receiver on our ship will receive frequencies from stations F, B, and E, and soon you will find out that you are between the countries of Trinidad and Tobago, Madagascar, and Argentina. The second step is to identify your distance between each station. The location from station X to station Y is based on the phase difference of the signal received from a pair of stations. When the ship is equidistant to both stations, there will be no phase difference. The system will present phase difference when the distance between two stations are different. The concept of phase difference is applied for the lane identification. The lanes are numbered, wherein the lanes are separated by 8 miles. However, you'll find 8 miles very inaccurate, so they divided it into 100 equal parts. In our scenario, we'll be having two pairs of stations. Stations B and E for the first one and F and E for the second one, wherein each pair will present line of position or LOP. First, we'll be having the pair of stations B and E. The meter will indicate the lane and will consider it as the first LOP. Second pair will be the station F and E. Also, the meter will indicate or find the lane number and will consider it as the second LOP. The point where the two LOP intersect is said to be the approximated location. Yes, we already know our location. However, it is not yet that accurate. So, we need to use correction table. Correction table must be used to take into account the changes in the ionosphere at different location, times of the month and day. Applying it to our case, let's assume that the correction for our current location and time is equal to a value of plus 4.04. So, the current readings will be added with that value. Now, we are certain of our current location. The next problem is to find the safe place. So, let's assume we have a table of lane numbers to know the safe place with respect to stations B, E, and F. In order to arrive at that place, you can monitor the readings until readings matches the required lane.